Now, I want to call back some of the language we learned yesterday, right? Y equals x squared. Is it a function or a relation? Bit of a trick question. Functions are special kinds of relations, aren't they? They connect two numbers, but more specifically, when you put in one x value, you'll get one y value out, okay? Now, we looked at different kinds of functions. What kind of a function is it? Is it one-to-one? It's not one-to-one, is it? It's many-to-one, or more specifically 2-to-1, because if I give you an output, a y value, you can give me two inputs, two x values that would give me that equally, okay? So it's not one-to-one, which is why you can't get an inverse function out of it like it is. What must we do to get an inverse function? I must do some kind of restriction, okay? Now when you look here, right, or rather when you look at the questions we've been seeing, right, they generally provide a restriction to you, right? They say, look, I only want this side or that side. When you look at it, I mean, it's literally symmetrical, right? I could restrict it in some ways any way I like, okay? What are my two options? I can say x is less than or equal to 0, which is over that side, okay? Or alternatively, I go the other side, okay? Now, by the way, the reason why it's 0, why 0 and not 1 or negative 3? Why is that the important point around which this turns? Well, number one, there's the symmetry. More importantly, though, this is a turning point, right? It's a turning point. So when I rotate this around, or reflect it rather, across the y equals x line, the turning point is what breaks the function, right? It's what turns it into a relation, okay? So anyway, that's the point I'm interested in. Now, it's arbitrary which one I pick. Both of them will give me an equally good inverse function, okay? So in some senses it's random, but in another big sense it's not random. Why is it that we only pick one side? When we're defining this thing, the inverse function, right? We only select one side and everyone agrees on which side to pick, right? Why do we pick one side over the other? Apart from everyone's agreed to. I guess the question is, why would everyone agree to? Let me ask you this question. This function here, this inverse function, where is it used? In what cases does it get used the most? Where's the first time you learn about it? Probably something like this, right? Coming back to the very first question we were looking at the other day, right? You learn this in Pythagoras. That's like year 7, right? So you learn, you want to work out this side here, and the square root's involved, okay? In this case, not such a big deal. But if I change number, you're like, oh, that's messy, right? So you get a surd, you get an irrational number, okay? But of course, it wouldn't make much sense to say, this is the square root of 34? Is it 34? Wouldn't make much sense to say that if we had defined the inverse function using this part of the domain, right? Because then you're saying it's a negative number. That doesn't make sense, does it? Okay. So why do they choose this, these values over here? Why do they restrict it that way? No, seriously, why do they restrict it that way? Because that's where we use it, right? That's where it's valuable to us. That's where it's practical, okay? So therefore, when we come to our problem, let's just take them one at a time. Okay, y equals sine x. Let's draw this guy. Let's draw him. And by the way, I know you're used to drawing him from 0 to 2 pi, not from 0 to 360 degrees. We're in radians today. But it's going to be useful to us to actually include some of the negative domain. You'll see why in a second. Is sine x 1-to-1? There is no more non-1-to-1 function than sine x, okay? There is an infinite number of solutions for every y value you'd like to put in there within the range, okay? Within the range. Whoops. Okay? So therefore, we're faced with exactly the same problem that we have. Here, we must restrict in some way, okay? Now, let's have a think about this. We are trying to come up with a definition for where this, the inverse function of sine, where it ought to exist. Okay. Now, I'll pose to you the same question I posed over here right? Which is, where do we use this inverse function? Where would it be practical to restrict it? Because we have a whole bunch of choices, don't we? Right? What kinds of values do you definitely want? Right? Well, again, you come back to these triangles, right? If you want an angle like this, okay, or like this, what kinds of angles are those? Number one, they're acute. Number two, they're positive, right? So, where are those angles? Well, thinking about acute angles, that there is pi on 2, isn't it? Pi on 2, okay? So we at least definitely want these angles in here. These are the acute angles, okay? So we want that little part of the graph to be part of our restriction, okay? Now, if you say, I want this part, that severely limits your options for how you're going to restrict the rest, right? For instance, can you get obtuse angles? Could we include that meaningfully in our restriction up here and end up with a function down here? And the answer is no, because where are the obtuse angles? They're here, aren't they? From pi on 2 to pi, okay? But the second you include those, you've either got the obtuse angles or the acute angles, because otherwise you break the one-to-oneness of the function, right? So it's just one or the other, right? Town's not big enough for both of them. And I think acute ones are going to be more useful to us, right? Are there any other values we could include? Well, I could go to the left of the origin, couldn't I? I could go all the way down to, now, how far can I go? What's that value there, right? Negative pi on 2. Now, why do I stop there? Because there's a turning point, right? Which is exactly the same reason why I stop over there, okay? So therefore, I now have this domain, okay? Which is a useful, practical way to restrict the function, the original function, from pi on 2, sorry, negative pi on 2, to positive pi on 2. That makes sense, okay? So if that's the domain up here, okay, it's going to become the range down here, right? X's to Y's. While I'm thinking about domain and range, what was the original range? The original range was from -1 to 1. Okay, so therefore that's going to be my new domain. Right? Okay, so what's this guy look like? Okay, I want to reflect him like I was doing before. Okay, like you saw was the useful way to do it. So this time, I want you to draw it again, but this time, number one, draw it bigger. Number two, let's just do the restricted part, okay? Number three, I want you to take care. Even this graph is not very good for this. We're going to reflect across what line? Y equals x, right? Now to make this look reasonable, I want y equals x to look like y equals x, right? So, I'm going to need to get this 45 degrees happening. Right? And the thing is, you know a lot about how x and sine x relate to each other, particularly there at the origin where they form the angle. Okay? What's the special relationship between x and sine x at the origin? Think back to when we were doing differentiation and we were thinking about the derivatives for the trig functions. They're tangent to each other there, right? So therefore, you're going to need your sine x to go off at 45 degrees, which we don't tend to draw it like. I certainly haven't drawn it like that here, okay? So when you're drawing your new one, which is bigger and is restricted from negative pi on 2 to pi on 2, just watch for that angle, okay? Let's draw it now and see what the reflection looks like. By the way, as you're drawing it, to help you with the scale, right? Because we're trying to get this 45 degrees happening, that means that the x scale and the y scale are the same. Does that make sense? Because if I squish or if I stretch, that's what makes it not 45 degrees, okay? So therefore, you actually know the values you're interested in. For example, if this is 1, right? What's the domain going to be? We said it was going to go to pi on 2. What's pi on 2? You know what pi on 2 is. It's a number. It's like 1.57 or something like that, right? So that should be 50% longer than this one. Should go further across. Okay, so that's. So at the very least, you need to have all of those markings there. You will not be able to draw this accurately without all of those, okay? So I'd recommend you start off by drawing your original function, okay? Just draw sine x, which is going to be locked in here and there, okay? So you're going to end over here and here, okay? Now to make sure you draw this accurately, you get the shape. Shape is everything. Shape is critical, okay? What's happening at the endpoints? Why didn't I select them as endpoints? Do you remember? They're turning points, aren't they? So therefore, here's the way I draw them in, right? I place my endpoints and then I say, well, I've got to have a gradient of 0 there, don't I? Right? Often when I'm drawing, if I draw from in here and I'm drawing down, I often don't end and get it right. You know, I end at a funny angle, okay? So by putting a horizontal line there, that's my visual cue to actually get there and make my shape accurate. Same thing happening over here. That should be horizontal, okay? And there's one more marker I have which said that it's going to be 45 degrees at the origin, right? So I'm going to draw a 45-degree angle in there, like so, okay? And now I can connect the dots. There you go. There's my sine x. All that work, just that one line, okay? But at least the shape is accurate. The curvature is accurate. Okay, now, oh, that's bad. Oops. Let's try that again. That green line, green dotted line, that's going to be the line across which I reflect this shape. Okay. Now, if you have another color, and I think I've run out, it will be really useful to you. So try and make them easy to distinguish. How shall I do it? I'm going to do it in green. Now, remember, everything is swapped. X's and Y's all swapped, okay? I have turning points, right, and horizontal tangents at these endpoints for sine x, right? Let me say that again. I have turning points and horizontal tangents at these endpoints for sine x. So therefore, for sine inverse, what should you expect if x's and y's are all swapped? Instead of horizontal tangents, right, you're going to expect vertical tangents, right? So just like I did before, I'm going to say if this is my endpoint over here, right, it must absolutely get to a vertical line. Right? If I don't, it doesn't represent what sine inverse looks like. Okay, and I'll do the same thing down here. Okay, I've already got this 45-degree angle in the middle that I need to get to. Okay, so I'm going to try my best to draw it in accurately and match all the features that I'm expecting. So close. Okay. There you go. Now, can we note a couple of things? Because of this domain restriction business, right, y equals sine inverse of x is not the same thing as x equals sine y, which is just swapping the x's and y's. Can you see that? What would it look like if I did draw x equals sine y? What would the difference be? remember what the difference is. I restricted here, right? I restricted here, which ended up with a restriction here. If I made no restriction, right, and just said, just swap it, right? Then I'm gonna get, this thing's gonna keep going, right? It's gonna keep going up and down, just like regular sine x keeps on going left and right, okay? So it'll stretch on forever that way. Its range will be all real values, just like the domain of sine x is all real values, okay? So please do not mix them up, right? It's not simply x equals sine y. Another way you can think about it is, you know, it's very close to this. You put in a value like, say, 1, okay? And what it gives you back is an angle, like pi on 2, okay? So if I say that, right, sine inverse of 1 is equal to pi on 2. That's what I read off the graph, okay? I could almost interpret that as saying, okay, sine inverse of 1 is the angle such that if I take sine of that, it gives me 1. Can I say that again? That's confusing. Sine inverse of 1 is an angle, right? It's the angle such that if I take sine of it, I'll get 1, okay? So that's the way inverses relate to each other, just like e to the x and log x, right?